Have you ever felt the ground tremble beneath your feet? Sometimes it's just a faint vibration. Sometimes it's a jolt that makes your heart jump and the whole room sway. If you live near the west coast on any tectonic boundary, that's the earth reminding us, I'm alive down here. Hi, I'm your Professor Farida Bucks Musa and welcome back to another lecture for your Physical Geology Class 001A at West Valley College. So what actually causes these ground emotions? Why do earthquakes cluster where they do? And why do some wreak havoc while others go almost unnoticed? Let's explore all these, and by the end, you'll know the science, the risk, and what to do to stay safe. Now let me pull up a map. Here's British Columbia, March and April 2015. What do we see? Over 140 earthquakes, big and small, scattered like breadcrumbs from the southern tip of Vancouver Island all the way north to Haida Gwaii and Fort St. John. Some are in clusters, some in lines, and some are outliers far from the coast. And let's start with those clusters of small to medium quakes beneath the Juan de Fuca and Explorer plates. These are not random. Right along the plate boundary, deep under the Pacific, the Earth's crust is splitting, grinding, and sometimes catching until snap. It slips, releasing energy as an earthquake. Some are so small we don't even feel them, but they tell geologists exactly where the tectonic action is hot. Now look at the Haida Gwaii, a string of little earthquakes lined up right next to where that massive magnitude 7.8 quake struck in 2012. What's happening there? Aftershocks. When a fault ruptures in a big way, the stress doesn't just vanish. It redistributes, and nearby rocks adjust over months or years, leading to a series of smaller quakes. Down closer to Vancouver Island, you'll notice most of the quakes are shallow. That's our old friend plate tectonics again. The Juan de Fuca plate is sliding under North American plate. This subduction creates enormous stress along the margin, and when that stress gets too great, the rocks break suddenly, causing earthquakes very close to the surface. And what about those strange earthquakes far north, around Fort St. John? Nowhere near a plate boundary. In that case, what you're seeing is human-induced seismicity. Activities like natural gas extraction and fracking actually change the stress underground and can trigger earthquakes. Proof that sometimes we actually wake the sleeping giant ourselves. So where do earthquakes happen? They overwhelmingly cluster along plate boundaries. At transform faults like San Andreas, you get lots of shallow, sharp shakes. At convergent or subduction zones, you get the really big ones, sometimes miles deep, often producing tsunamis. Subduction zones, in fact, are where the greatest earthquakes in history have been recorded. Every time you hear about shaking along the Pacific Ring of Fire, you're hearing about Earth's tectonic plates at work. But if you want to understand earthquakes, you also have to understand seismic waves and how we measure them. Earthquakes release energy that radiates out in waves. P waves are the fastest. They are compressional, like the slinky you push and pull quickly. S waves are slower and move like shaking a rope side by side. Both move through the earth, but when they reach the surface, they transform into surface waves, Love and Rayleigh waves that make the ground heave and roll and do the most structural damage. How do we measure these shakes? The most common number you hear, the magnitude, means the amount of energy released. Whether it's called Richter, local magnitude, or moment magnitude, it's a measure of how much the earth moved and how hard. It's all based on seismic records. A magnitude 5 earthquake shakes out 32 times the energy of a magnitude 4. Yes, it's logarithmic, so every step up the scale is steep. But while magnitude reflects total energy, earthquake damage depends on something else too. That's intensity. Intensity maps how a quake was experienced or felt at different places, and it's hugely dependent on ground type, distance, and the structures built there. The modified Mercalli intensity scale is all about real world consequences. If you felt like mild swaying, saw cracks or toppled chimneys or complete collapse, it's all intensity. varying block by block. Now, let's make it vivid with a story. In 1985, a magnitude 8 earthquake hit the Michoacan region of Mexico, around the epicenter. Surprisingly, little damage. But in Mexico City, 350 kilometers away, the destruction was catastrophic. Now, why, you may ask? The entire city sits on the soft, saturated sediments of ancient Lake Texcoco. When seismic waves rolled in, those sediments acted like a giant bowl of jello, amplifying the shaking, especially for taller buildings that naturally swayed at the same frequency as the ground. It was resonance, the same principle as opera singers used to shatter a glass. For 2 minutes, multi-story buildings swayed back and forth, floors pancaking, windows exploding. That's not about magnitude, it's about intensity, geology, and resonance. Closer to home, recall the 1989 Loma Prieta earthquake near San Francisco. Areas built on soft mud, not solid rock, saw elevated destruction. Parts of the double-decker Cypress freeway simply collapsed, while neighborhoods right next door, built on bedrock, held up far better. Earthquakes rarely limit themselves to just shaking. In a big event, expect a cascade, landslides, slope failures, liquefaction, even tsunamis. Here's how liquefaction works. During violent shaking, water-saturated sand loses its strength and behaves like a liquid. Buildings can suddenly tilt or sink. Pipelines can pop out of the ground. Roads can buckle. It's dramatic and terrifying to witness. Then there's fire. The 1906 San Francisco earthquake, famous for leveling a city, actually did most of its damage to flame, not shaking. Ruptured pipelines and snapped power lines sparkled massive blazes, while broken water mains left firefighters helpless, watching entire neighborhoods burn. And after the shaking, after the aftershocks, come stories of people working together, rebuilding, and sometimes stories of lessons learned the hard way. Turkey, for instance, suffered huge losses in 1999 Izmit earthquake despite having strong seismic codes, because buildings weren't constructed or inspected carefully enough. After another big quake 2 months later, the government clamped down. But as always, enforcement is key. This brings us to preparedness and mitigation. While we can't predict exactly when or where the next earthquake will hit, we can forecast risk. That's why places like British Columbia are investing in seismic retrofits for schools and hospitals, especially in the lower mainland and Vancouver Island, the most vulnerable regions. In some places, P-wave early warning systems allow critical infrastructure to shut down seconds before strong shaking arrives. Such a window may seem small, but it can save lives and prevent disasters from derailing trains to cutting gas lines. For individuals, the best defense is knowledge and planning. Know your escape routes. Keep food, water, medical supplies, and a flashlight handy. Make sure every household member knows where to meet and whom to call. Practice drop, cover, and hold on. And don't count on using your cell phone when everyone else is trying to call at the same time. So what's really happening deep below when the earth shakes? Imagine two pieces of crust slowly being bent by tectonic forces, resisting for years, maybe centuries, building up stress. Suddenly, the fault slips. The rupture starts, maybe kilometers underground, sending radiating waves outward. That first break is called the hypocenter, the spot directly above the epicenter. The shock can then zip along the fault for dozens or even hundreds of kilometers, with aftershocks jostling the rocks as stresses are transferred along the fault. And in some subduction zones, like those off our Pacific Northwest coast, a process called episodic tremor and slip sometimes happens. Here the fault doesn't always slip suddenly, but rather in slow, quiet quakes over weeks, barely felt but shifting the earth all the same. Now let's summarize and pull it all together. Earthquakes are natural, inevitable consequence of our dynamic tectonic planet. They cluster at plate boundaries, occasionally strike in plate interiors, and can even be triggered by human activity. They are measured by magnitude, the total energy, and by intensity, the experienced shaking and damage. Their impacts stretch far beyond the shaking itself. They tear down buildings, start deadly fires, trigger tsunamis and landslides, and can devastate infrastructure. Although we cannot predict earthquakes precisely, we can minimize their impact through science, engineering, policy, and smart personal action. Good building codes, effective emergency plans, and a prepared, informed public can mean the difference between tragedy and resilience. So the next time you feel the earth tremble, remember, it's not just random chaos. It's the result of deep, powerful, but understandable forces at work far below your feet. Understanding those forces and preparing for their effects is one of the best investments you can make as a citizen, a family, and a community. Thank you so much for joining me in today's lecture. Make sure, again, you do your exercises, you do your assignments, you do a great job with your lab, you make sure you attend your labs in person, and if you have any questions, attend my office hours every Friday between 2 to 3 p.m. Or if you have any questions, send me a message, send me an email. I'll see you in the next one.